Hello friends, in this video I'd like to solve the following problem from the Iranian Mathematical Olympiad, final round year 2008. Combinatorics problem number 3, because this Olympiad, as I have seen, is divided into branches of mathematics, and on each branch there are several problems. A link will be in the video description. So we wish to prove that for every natural number n, the following equality holds, namely, sum which goes from 1 to n of n plus k minus 1, choose 2k minus 1 equals f of 2n, where f of 2n is 2nth Fibonacci number. The very famous Fibonacci sequence appears in this problem. So my hints for this problem, it's a bit tricky. But my hints will go as follows. First of all, it should be pretty obvious, but if two sequences satisfy the same recursive relation with the same initial conditions, they must be the same sequence. They must be equal. Every term must be equal. So nth term of one sequence must be equal to nth term of the other sequence. Of course, if recursion is well given. Then recall the recursion for Fibonacci numbers. F of n equals the sum of previous two terms with boundary conditions, initial conditions. F of 0 is 0, f of 1 is 1. And recall also that our binomial coefficient, r choose k, is by definition, there are many definitions, but it's one of them, is r times r minus 1 times r minus 2, and so on, up to r minus k plus 1 all over k factorial, if k is a natural number from 0, and if the lower part of our symbol is negative, then it's 0 by definition. And crucially, this property will be used many times in my reasoning. R choose k equals r minus 1 choose k plus r minus 1 choose k minus 1, and that works for every integer k and for every real number r. It's crucial. And also, to simplify your reasoning, because we will have to shift our index of summation, you may want to consider sum going all over all integers. Because if you step into negative integers, your lower part of binomial symbol, binomial coefficient, will become negative, and this binomial coefficient will go to 0. And moreover, if k is too big, the upper part will be less than the lower part. They both will be positive integers, and so this also will be 0. So you may want to extend this sum in both directions, to minus and to plus infinity. So give this problem a try, and I will see you in a minute. Okay, so here comes my solution, my idea. Well, let's start with finding recursion for Fibonacci sequence, but only with even indices. So let's take a look. F of 2n is, by definition of Fibonacci sequence, it's f of 2n minus 1 plus f of, or maybe, you know what, f of 2n minus 2 plus f of 2n minus 1. Okay. This index is even, but this is odd. So what can we do? Well, we can use our recursion once again. So it's f of 2n minus 2, f of 2n minus 2 plus, what is f of 2n minus 1? Well, it's f of 2n minus 2 plus f of 2n minus 3. So we have 2 times f of 2n minus 2, and we have 2n minus 3. Again, index is odd, so we want to roll our recursion. So we have f of 2n minus 4 plus f of 2n minus 5, and again And again, you probably see the pattern emerging. After many applications of our recursion, we will have 2 times f of n minus 2 plus f of 2n minus 4 plus f of 2n minus 6. We'll be going all over even indices, and we will finish at, let's say, f of 6, f of 4, f of 2, and finally f of 1. But what is f of 1? F of 1 is just 1. Okay, so now we have a recursion for the sequence of Fibonacci numbers with even indices. It's a rather lengthy recursion because we are going all back to the first terms. 2nth term equals this sum, and also this recursion is properly given because we also know that f of 0 is 0. So together, so you know what, maybe I will write it again. So f of 0 equals 0 and f of 2n equals 2 times f of n minus 2 plus f of 2n minus 4, f of 2n minus 6, and so on. F of 6, f of 4, f of 2, and finally f of 1, and that obviously holds for positive, that holds for positive integers. Okay, very well. And now what I will try to do is to show that our sum satisfies the exactly same relation. Exactly the same relation. How can we do it? Well, first of all, let's consider denoting our terms of our sum. So let S of n equals sum which goes from 1 equals k equals 1 to n. Let's look back. N plus k minus 1, choose 2k minus 1. N plus k minus 1, choose 2k minus 1. And I will show that the exactly same relationship is satisfied for every natural number starting from 0. So first, let's take a look of s of 0. So s of 0 is sum which goes from 1 to 0 of k minus 1 to k minus 1. And we know that since the lower index is less than the upper index, this is empty sum, and empty sum is by convention, it's by convention 0. So okay, f of 0 really equals s of 0. So our initial condition is satisfied. And now let's take a look finally at s of n, which goes from 1 to n plus k minus 1 to k minus 1. As I suggested, to make our life easier, I will consider this sum all over integers in both directions, from minus infinity to plus infinity. Is it legal? Yes, it is, because if k is negative, as I said, this part is negative, and n choose negative number is by convention 0. And if k is greater than n, let's take a look. If n is greater than, if k is greater than n, then 2k is greater than n plus k, and 2k minus 1 is greater than n plus k minus 1. And again, upper part of binomial coefficient is less than the lower part. So also in that case, n plus k minus 1 choose 2k minus 1 is also 0. It's not by convention, but it's by definition. Because if you recall, we have falling powers in the definition of binomial coefficient, and this product of falling, of going, n plus k minus 1, n plus k minus 2, n plus k minus 3, and so on, we will have 0 in this product. And 0 in this product will make our binomial coefficient to be 0. So in other words, this lengthy explanation justifies this equality, that it really can be done. It's justified. Okay. So we know that S of n equals sum going over all integers n plus k minus 1, 2k minus 1. And now what I want to do is to use recursion for binomial coefficients, because n plus k minus 1 is the same as n plus k minus 1 minus 1, choose 2k minus 1, plus n plus k minus 1 minus 1, choose 2k minus 1 minus 1. And I will split it into two different sums. So first sum will be n plus k minus 2 over 2k minus 1. And the second sum, or you know what I will do? Maybe I will write the first binomial coefficient in this way: n minus 1 plus k minus 1. And second will be sum over integers of n plus k minus 2, 2k minus 2. If you look closely, this sum, since we have n minus 1 here instead of n, this first sum, it's just s of n minus 1. Okay, now that's something. And what can we do with the second sum? Well, with the second sum, we can do exactly the same. So we can take this sum and use recursion for binomial coefficients. So it's n plus k minus 3, choose 2k minus 3 plus n plus k minus 3, 2k minus 2. Okay? And now let's split it into two different sums. K goes over all integers. The first part, let's take a look. The first part is n plus, I will write it in this way, n minus 1 plus k minus 1 minus 1, choose 2 times k minus 1 minus 1. Okay, very nice. And the second sum will stay the same for now. So it's n plus k minus 3, 2k minus 2. Okay. And now let's notice that simply by shifting our index of summation in our first sum, changing k to k plus 1, we will get sum also over all integers, n minus k, n minus 1 plus k minus 1, 2 times k minus 1. So I have just shifted my index of summation by one position, and that is why I have suggested to consider our sum all over integers, because we need not to worry about, you know, going from 1 to n or from 0 to n minus 1 and blah blah blah. Okay, and what about the second sum? Well, I will use my recursive formula for binomial coefficients once again. So I will have n plus k minus 4, 2k minus 3 plus sum which goes all over integers. But I need some space. N plus k minus 4, 2k minus 2. Okay. And let's take a notice. This first is s of n minus 1. The second sum, if you look closely, n minus 1, it's also s of n minus 1. What about the third sum? In the third sum, I will again move the index of summation, but this time I will move it by I will put k plus 1, yes. Instead of k, I will put k plus 1. And if I put k plus 1 instead of k, I will have the following. N plus k plus 1 minus 4, 2 times k plus 1 minus 3. And let's leave our last sum as it is for now. And what do I have? Well, here I have 2 times s of n minus 1, and my sum can be written in the following way. It's sum over all of the integers, n minus 2 plus k minus 1, choose 2k minus 1, and let my last sum stay the same. So we have 2 times s of n minus 1, and look closely, this sum, since we have n minus 2 here, the second sum is s of n minus 2. That's something, because look, here we have 2 times n minus first term plus n minus second term and something else. If you look back at the recursion for Fibonacci sequence with even indices, very similar thing is going on. So that gives us hope. That should give us hope. And what will I do now? I will do it again. I will take my sum and I will use recursion. So I have n plus k minus 5, 2k minus 3 plus sum over integers, n plus k minus 5, 2k minus 2. So I have 2 times s of n minus 1, s of n minus 2. In this sum, what will I do? Again, I will move my index of summation by 1. So instead of k, I will put k plus 1. So instead of k, I will put k plus 1. And my last sum will stay the same for now. And look, here I will have sum which goes over all the integers, n minus 3 plus k minus 1, 2k minus 1 plus this sum which goes from all over the integers, n plus k minus 5, 2k minus 2. Look closely. N minus 3, so that is our n minus third term. Plus our sum. And I hope that you see the pattern. I need some page. This problem is quite lengthy. And I hope that you see the pattern. In my next step, I will have 2 times s of n minus 1, s of n minus 2, s of n minus 3, s of n minus 4, and the last sum will be different. If you look back, the last sum differs only in one respect, namely, for example, look here. Every time the last sum, here we have minus 4, now we have minus 5. Then we will have minus 6, we will have minus 6 over 2k, choose 2k minus 2, and so on and so on. In the end, my recursion will go back right to the end, or maybe right to the beginning. I will have that, and so on. And I will finally have what exactly? S, let's say S of 2. And I will have S of 1. And finally, I will have sum which goes all over the integers. Of what exactly? Well, how to know it? Look, here we have n minus 4, and here we have n minus 6. This part is always differs from this quantity by 2. So if I have 1 over here, I will have in my sum not 1, but minus 1. I will have k minus 1, 2k minus 2. Okay, very well. And now let's take a look. So you know what, I will copy the first part. I will copy the first part. And let's take at our final sum. What is it? Well, if k equals 0, so let's write for now a question mark for the last part, and let's work it out. K minus 1, 2k minus 2. I will split it into 3 different sums. One will be over negative integers. The second one will include, over integers, negative integers or 0. The second will be for k equals 1. For k equals 1, we have 0, choose 0. And then we'll have our sum from 2 to infinity of k minus 1 of 2k minus 2. And let's take a look. The first part, it's just 0. Why is 0? Well, because the lower part of binomial coefficient is negative. So this is by definition 0. 0 choose 0 is 1. And this sum, let's take a look, both indices are positive, but this time the lower part is greater than the upper part. So it's 0, not by definition, but by computation. It's a well-known fact. So, would you look at that? The last term is 1. So we have the following recursion for our sum. S of 0 equals 0. S of n equals 2 times S of n minus 1. S of n minus 2. S of n minus 3. And so on and so on. S of 2, S of 1 plus 1 for positive integers. Moment of truth. Now is the moment of truth. Let's take a glance at the recursion for Fibonacci sequence with even indices. Let's copy it. Let's put it side by side. Exactly the same. Exactly the same. Our sequence starts from 0 and recursion is exactly the same. And that means that, alright, since f of 2n and s of n satisfy the same recursion with the same initial condition, they must be equal. i.e., let's write our result triumphantly. That means that our sum, which goes from k equals 1 to n plus k minus 1 to k minus 1 equals the 2nth Fibonacci term in Fibonacci sequence. And that closes our proof. That proves it. Okay, so a few comments before we go. First of all, it's probably also possible to show this by induction, but I have a feeling that the proof might be a bit hairy, a bit ugly at some parts. What else? It also might be possible to prove this result by generating functions, because this sequence has a nice generating function, but to be honest, I have not investigated it that much. What else can I say? Well, one more thing. In our problem statement, it was stated that this sum should be equal to this. So our problem was much simpler because we have, what can we say? We have already been spoiled what the result should be. So we have just compared relations, recursions for Fibonacci sequence and for our sum. It was much simpler. It would be a much harder problem if we are just given this sum. Question is, what is this sum? It would be much harder. The only hope. So let's imagine that we are given this sum. We don't know what to do with it, and we are asked what the closed form, what is the exact value. What can we do? Well, to be honest, the one thing to do is to write first few terms of our sum, for example, for n equals 0, for n equals 1, for n equals 2, 3, or 4, and then try to see the pattern. Once you see, for example, because this sequence, if you know Fibonacci sequence, which goes 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. And if you see, for example, sequence which begins with 0, 1, 3, 8, 21, bells might start ringing in your head that it might be connected to Fibonacci sequence. But that is also problematic because, well, the more you study discrete mathematics, the more you prepare for competitions and so on, maybe the easier it becomes, but I guess that not many people know by heart which sequence should be investigated by looking only at the first few terms. So it's partly art, partly science. Okay, so I will stop rambling. Thank you for watching. I hope that you were entertained, and I will see you soon. Goodbye.